In this video, I'd like to walk through an exercise of mapping out the microinstructions, the microcode, the timing steps of a simple machine level, assembly level instruction of load the accumulator. And this is the version of load the accumulator where the instruction will have an opcode and an operand, the operand being the piece of data. In this case, the data is an address, and then the value at that address in memory is what we want to put in the accumulator, which is the register associated with the ALU. Okay, so in this, we have a very simple toy architecture here shown in the picture, in the green and the yellow. And it's going to be sort of a von Neumann type architecture. And what I want to emphasize there is that in memory, we will have both instructions and data. So to perform this instruction, we're going to have to access memory twice, once to get the instruction, and then the second time to get the data to put into the accumulator. So I want to talk about a little analogy about accessing memory, just because I have a bunch of students who work in restaurants, so this sort of sometimes helps them. That when you're dealing with memory, it's random access memory, you provide an address, and then you get the value at that address. So that's how memory is, that's how RAM is organized, that's what we mean by it. We're going to supply an address and then get the value at that address. And so when we're dealing with memory at this very low micro instruction level, there are always two steps. One is to prepare the address, and then the second then to either, sometimes we're writing the value, sometimes we're reading the value, but to deal with the value. So first address, then value. And so I liken it to a restaurant in that the addresses are like the restaurant staff. They arrive earlier. They must arrive first. You can't have customers in the restaurant if there is no staff. So the addresses like the staff arrive first, and they typically use a different entrance if it's a fancy enough restaurant. So they will have some staff entrance. So in our analogy, in the architecture, we're going to have an entrance to memory for addresses, the memory address register, and we will have a separate place to deal with the values, the memory data register. And so if the addresses are like the staff and the values are like the customers, they arrive later and they use their own entrance, different entrance. Okay, so much for the analogy. Okay, so in this exercise, we're going to do two things to sort of see if we understand the mapping of this instruction. We're going to say what's involved. Things may be actively involved or passively involved, but we just want to say all over who in this architecture has anything to do with it. It's a bus architecture, so there are devices putting things onto a bus, things taking things off of a bus. Putting things onto a bus is usually known as enable, and reading things from a bus is load. And we want to see who's got an enable action, who's got a load action. So these things should also appear over here in this list. So we want to see if we understand it that way. And then we also, we've labeled the interactions between various devices and the bus, or parts of, say, memory, the address register with memory, or the data register with memory. We have just sort of labeled these arrows. And so in another part of the exercise, we will sort of show all the number of the arrows to sort of see the flow. So not just who's involved, but what's the flow of things. And so in the first step, we don't yet have the instruction. We are getting the instruction, and the device then tells us where the next line of the program to be executed is. That's the job of the program counter. And so we're going to move the value of the program counter into the memory address register. But the first thing I'm going to do in terms of active involved is say there's always control. Control's always doing something. So the first thing I'm going to write down is control. And that's always there. So I'm just writing control, 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 control. Always there's some control going on. Okay. And then in this first step, we said that the program counter is taking its value out onto the bus and it's going into the memory address register. So the program counter has the address, but to get that address, to get the value at that address, we need to use the memory address register. That's who talks to memory. So who's involved? I'm going to say PC for program counter and MAR for memory address register. And then if I'm specifying who's putting something onto the bus, who's driving the bus, who's enabled, that's the program counter, and who's reading from the bus, that was the memory address register. Okay, and then if I use my arrows, in this, there would be a connection of control to everything, because everything needs to be controlled, and it's like just too many things, so I don't have those arrows drawn. But of the arrows I do have drawn, I've used 4 and 6. Okay, so that was step 1, to get the address out of the program counter into the memory address register. Okay, in step 2, we are going to get ready for the next instruction. In linear programming, we're going to assume is the next instruction in memory. And so we're going to prepare for that by incrementing the program counter. And the program counter by the name counter knows how to increment. So we don't need to run over to the ALU to know how to add 1. The program counter is a device that just has to be told to increment and then knows how to do that on its own. So the program counter is involved. We already said control is involved. So the control sends a increment signal to the program counter. And so there's no bus involved. So there's no enabling or loading from the bus in that step. And we don't have any arrows from control. So there is some flow, but not in our little naive picture. Okay. Now in the third step, now from step 1, we have the address of the instruction loaded into the memory address register. We're ready to read that value in memory. We have the address telling us where in memory, then we're going to take the value at that location, move it through the data register, and what we're reading at this time in memory is an instruction, so we will put it into the instruction register. So the memory register is pointing to a location in memory, then that value in memory is moving through the data register onto the bus and into the instruction register. Okay, so who's involved? Control. The memory address register is providing the address, the memory. I'll just say mem, but I could say RAM. That would also make sense. And then the memory data register takes that value from the memory and it gets moved onto the bus. And I tend not to write bus, but I could. In this active involved, the bus was involved in 1 and 3, if you will, but I didn't write that down. And then the instruction register. So I'm going to write IR. Okay, so that's who has some role in this, who put something on the bus. That was the MDR. and who took something off the bus. That was the instruction register, IR. And what was this sort of flow? 7 provided the address. 9 moved the value. So that if I'm talking about my restaurant analogy, 7 was the entrance to memory of the staff, the address, and then 9 was the customers. So 7 and 9, the address, the staff and the customers. 7, 9. Then we're moving 10 onto the bus and 13 into the instruction register. Okay, and those all together are the, where am I at? That's what I want. I want to say that these are all that blue section I just made, that is the fetch cycle. So if I were to give you another exercise like this, that fetch cycle is always the same. So these first 3 rows, you would always fill in the same for this architecture anyway. Okay, so now we will begin the execution cycle. And so now the instruction, now we know what the instruction is. It's in the instruction register. And so we're going to add down here all these controls involved, but in the execution cycle, the instruction register is always involved. Because now that we're executing instruction, we need to know what it is. And then I have an arrow. I have an arrow for that, 14. So I'm going to put a 14, 14, 14 down here just to say there is flow from the instruction register to the control during the execution cycle. Now, what in particular is step 4 doing? This is a load direct accumulator A. So an instruction consists of an opcode and an operand, sort of an action and a piece of data. The operand, the piece of data in this instruction, is an address. And so we will move an address into the memory address register. So I have part of my instruction, at least, is data. Is the part of my instruction that is data happens to be the data is an address. And I'm going to move that address onto the bus and into where I put addresses, the memory address register. So I have, in addition to the 14, down here, if I'm following my flow, there's a 12.6. And then let's say who's involved. The instruction register is involved, 1, because I need to know what instruction I'm executing, but also it is playing a dual role, telling me what the instruction is, but also placing its value, it's being enabled and putting its value onto the bus. I'm not going to write it twice, but it is playing at this time a dual role. And then that value is being taken in, being loaded into the memory address register. Who put the value on the bus? Instruction register. Who took something off the bus? The memory address register. And I already did the flow, the 12.6. So that was step 4. Now, step 5, I set up the address. Again, my restaurant analogy, I have the staff have arrived, the address is there. And so now I have my restaurant staffed and I'm ready for the customer. So I'm ready for the value. And so I'm going to take that value I'm now pointing to and move it to the accumulator. So the memory address register is telling me where in memory. This time it's not an instruction, but data. But memory doesn't know that. The execution, the control knows what to do with it. But as far as memory is concerned, it doesn't distinguish between instructions and data. But the memory address register is pointing to a line in memory. I'm going to take the value. I'm reading that value. So I send it out. I'm sending it out through the data register. And I'm going up into the accumulator. So who was involved? The memory address register supplies the address. the memory supplies the value at that address. It moves through the memory data register, and it's moving into the accumulator. And again, I tend not to write bus, but I could. Who put something onto the bus? The MDR. Who took something off the bus, this time the accumulator? What was the flow? In addition to 14, to know what the instruction was, there was an address being supplied by the MAR, the data moving from memory to the MDR through 9, going onto the bus through 10, and going into the accumulator 15. So that was step 5. In this sort of architecture that we're pretending to talk about here, we're going to have other instructions which are more complicated than load accumulator. Say load indirect accumulator would be an example. And so this instruction is less complicated. It has accomplished its goal in 5 steps, but we're imagining that we want all the instructions to take the same number of steps in this very simple toy architecture. And so then the last step is to do nothing. So we need to know to do nothing. So in this sort of involved sort of vocabulary, we're saying the instruction register and control are involved, that they know to let everybody else rest. But there's no bus action on or off the bus, and nothing in these terms of these yellow arrows other than 14. So that's what I wanted to tell you, to sort of how to do this exercise and think about these steps and sort of show the flow, and also give you my little restaurant analogy. That's all I wanted to do here. Thank you very much for your attention.